Good afternoon. I'm Ross McGowan. I'm a corrective action engineer in continuing airworthiness at Transport Canada. Our passion is to identify safety hazards and collaborate to get them under control before they do harm. Today, I'd like to share some information with you about a very specific risk. Then I'm going to ask for your assistance in getting it under control. Finally, I'm going to challenge some of the assumptions you may have about standard fasteners. More than 5 years ago, aviation professionals in several countries recognized a problem and took action where failures of simple hardware was creating unacceptable safety risk. Transport Canada has been collaborating with the FAA, EASA, industry, and technical specialists to assess this threat and determine if we need to do more. I'm going to share some data with you about failures of standard hardware that convinced us that our actions to date have not been sufficient and we do need to do more. And we need the help of aerospace professionals like you to ensure that we find all the risk, and just as importantly, to make sure that the actions we take are limited to only those situations where safety is threatened. Regarding terminology, I think you will understand most of the language in my presentation today. However, there's 3 items I'd like to be clear about. A standard part is one that's manufactured in conformity with industry or government specification. A critical application is a mechanical or structural assembly that includes fasteners whose failure could result in an unsafe condition, either from a single fastener failing or from multiple fasteners failing from a common cause. And an SDR is a service difficulty report. Aliases. When I use the term self-locking nut, please hear prevailing torque nut because that's what fastener experts prefer to call nuts that are designed not to loosen. Standard parts are trusted travelers in the civil aviation supply chain. They're exempt from many controls because we believe we can rely on them. We're going to focus on 2 families of nuts. They're virtually identical. I'll refer to them collectively as the MS parts. They're MS21042 and NAS 1291 families of nuts. As part of our work to assess this hazard, Transport Canada had a look at the SDRs in our database. This included 11,000 standard part SDRs, all with NAS or MS part numbers. The next slide will give you a picture of this SDR data. It represents a fraction of what's actually occurring in the civil aviation fleet. We know that these service difficulties are underreported, and at the moment we only have access to Australian, American, and Canadian SDRs. SDRs about standard parts are a tiny fraction of all SDRs. That's the pie chart in the top left. Standard fasteners are about 1/3 of all standard part SDRs. That's the pie chart on the top right. Over the past 4 decades, there's been a gradual reduction in standard fastener SDRs. And during this time, the fleet grew a lot. So in fact, the situation is improving. In the Pareto chart in the bottom right-hand corner, we found that 20 families of standard fasteners are responsible for 2/3 of the SDRs. 2 families of self-locking nuts in particular caught our attention, and I'd like to tell you what we found. So MS21042 and NAS 1291 are strong, light, inexpensive, and readily available. It's not surprising they're widely used in aerospace, particularly on helicopters. In a way, each of those desirable characteristics creates a vulnerability. The strength of these parts derives from the high hardness level they're heat treated to, and that makes them vulnerable to hydrogen embrittlement. They become lightweight by having a very thin wall, and that introduces the risk of cracking when they're crimped. So here's how the hazard gets built into the part. The part's crimped to produce an oval shape, so the top left picture is a crimp mark. And that produces the oval shape that you see in the center top photograph. That spring loads the nut to grip the bolt threads, but it can also create cracks in the part that are, some of them will be too small to detect, and that's the top right-hand photo. And then the bottom photo is a cross-section of a part, and I don't know if you can see the silver-colored cadmium plating. It's during the cadmium plating that the hydrogen will infiltrate the part and migrate to the areas with high residual stress, like the crack tips. The vast majority of the MS parts don't fail in service and create unsafe conditions. There's literally tens of millions of these things flying today. We've concluded that in addition to the inherent flaws in the part, additional risk factors must exist. These could include the fastener being a single point of failure, the fastener joint being loaded in tension rather than just shear, frequent removal and installation, bottoming of the nut on a bolt thread, severe environmental conditions, poor quality, and maintenance error, for example, over-torquing of the nut when it's installed. These are the service difficulty report history for these two families of parts. The bar chart shows the history of SDRs going back 40 years or so, a total of 155 occurrences. The MS21042 SDRs are in blue and the NAS 1291s are in orange. Please remember, these reports are just a fraction of what's actually occurring. So how did the nuts fail? 70 of the reports described a nut being split or cracked, and that's almost half of the SDRs. 38 of the nuts were found loose. 22 of the nuts were missing. Not sure why they were missing in each case, but the nut's certainly not doing its job anymore if it's not there. It may have split or loosened for some other reason. Almost 3/4 of the SDR had an immediate or potential impact on safety. A quick case study. This is our poster child for standard hardware risk. Helicopter tail rotor drive system. We have 9 occurrence reports that identified missing hardware from the tail rotor drive shaft coupling as the cause. Now, these aren't SDRs I'm talking about, they're NTSB and other accident investigation reports. As most of you probably know, when you lose tail rotor drive on a helicopter, you must immediately perform an emergency auto rotation on landing. There is one exception. If you're in forward flight, you may be able to complete a run on landing. In 6 of these 9 occurrences, the helicopter was in forward flight. However, only 3 of the run-on landings were successful. The missing nut wasn't recovered from any of these occurrences, so we don't know exactly what led to the failure, but we do have some knowledge of the risk factors. One of them is that this installation resembles an old-fashioned string of holiday lights. Failure of any of the 28 nuts will result in loss of tail rotor drive. So when you lose one of those fasteners, you're no longer passing torque through that system. There was one additional occurrence, but this one had a happy ending. In 2016 in Australia, a cracked nut was found on a helicopter Thomas coupling, and that almost certainly prevented the 10th occurrence. Industry has been very active in mitigating risk from standard fasteners in general and MS20142 in particular. Most OEMs and many maintenance organizations have policies and procedures to assure the quality of the hardware that they purchase. And the OEMs have often issued bulletins to their customers and suppliers to extend those controls upstream and downstream. There's also been a more robust version of MS21042 developed, the MS21042B. And there's a 12-point corrosion resistant steel nut, NAS 9926, that's been developed to replace MS21042. Bell has replaced MS21042 with NAS 9926 on all of their production programs and has encouraged their operators to accomplish this change in the field on an attrition basis. And Robinson has replaced MS21042 with a type design part at some critical locations on all of their models that are in production, and they've also encouraged their operators to accomplish this change in the field on an attrition basis. Civil aviation authorities have also intervened. In several instances, we've required mandatory inspection and replacement with a different part number. EASA has issued 11 airworthiness directives along these lines. The FAA has issued 7. Israel has issued 1, and Transport Canada has also issued an AD like this. We've also taken some non-mandatory corrective action. We've published alerts and safety bulletins. In these bulletins, we recommend that the MS parts get tested for embrittlement before they're put into stock, inspected for cracks and other defects before they're installed, and checked periodically after they're installed to ensure they're intact and still in place. Is that how you'd expect a trusted traveler to be treated? So we've done a lot of things already, but we need to do more. Why? We don't think we've identified all of the vulnerable installations, and we can't continue to rely on inspections to prevent failure. Transport Canada has already contacted Canadian type certificate holders with a letter to inform them of this hazard. Rotorcraft and transport category fixed-wing TC holders have to perform a risk assessment and respond to us in 6 months with what they found and what they intend to do about any unacceptable risk. The other TC holders have been encouraged to perform an assessment, but they're not required to report back to us. EASA has taken the same approach, and they've extended their outreach to foreign certified TC holders with product that's operating in the EU. The FAA at this point in time is monitoring the situation. They've concluded that their corrective action to date have been sufficient. To mitigate this risk, we also need to look forward. We need to ensure that risks from standard fasteners are mitigated in new designs. This may include production and maintenance organizations knowing how to avoid introducing the hazard by, for example, purchasing from only qualified suppliers. EASA has issued certification memo CMS 003 and is applying certification review items to new projects. Transport Canada is still working on a plan in this area to mitigate future risk. We're considering an advisory circular to provide guidance. You might think that all of the actions that have been taken to date or the ones that are in progress would be enough to mitigate risk from standard fasteners in critical locations. However, there are residual risks involving standard fasteners in critical installations that we need to deal with over the long term. I guess I would also let you know that some of these residual risks affect type design parts just as surely as they affect standard parts. Some of these risks are associated with assumptions and customary practices that many of us have become comfortable with. I don't know if any of you have heard of the term the normalization of deviance. I think that's one of the things when a lot of us have been in the industry for quite a while, take certain things for granted. Accident investigations where the cause is not determined. We really need to learn more, at least the probable causes from accidents that involve standard fasteners. The reuse of self-locking nuts. Fastener experts have told us it's not prudent to reuse self-locking nuts where failure could jeopardize safety, but it's standard practice and endorsed with guidance material in civil aviation. Some civil aviation organizations already prohibit this practice. Environmental hydrogen embrittlement, where hydrogen infiltrates installed hardware, is something we're just starting to understand. We may need to replace some hardware before a certain age to reduce vulnerability in this area. The use of self-locking nuts without a secondary locking device, such as a cotter pin, where failure could affect safety, isn't permitted by our current standards. But there's many examples of this in service on older designs. For example, tail rotor drive shaft couplings. Hydrogen embrittlement failures continue to occur. How do we reduce their frequency with better process controls during manufacture of standard hardware? Lack of oversight of standard fastener manufacturing and in-service performance. Compared to type design parts, standard fasteners have nowhere near the same level of oversight. And finally, inadequate disclosure of nonconformance. Again, compared to type design parts, standard fastener manufacturers have nowhere near the same level of obligation to report suspected nonconformances. So in conclusion, we've covered a lot of material in the last few minutes. I'm hoping you'll take away the following messages. First, there are some installations that use the MS part that pose an unacceptable risk. Let's work together to identify those and get the risk under control. It's better to be proactive than reactive. Second, even after we collaborate on this project, there's going to be some residual risks that require our attention. Are we ready to start discussing which of those residual risks offer the most leverage for our next safety gains in this area? With this information in hand, please reflect on the in-service product you're responsible for that may be too vulnerable. For new designs, modifications, and repairs, please avoid using the MS part where a failure would adversely affect safety. And finally, please keep those residual risks in mind as you go about your rotorcraft work. I'm hoping we'll continue to talk about them for a while and then start doing something about them. I can't thank you enough for your time and attention this afternoon. I'd be pleased to try to answer any questions that you've got at this point in time.